I'm going to start with my usual question, which is, do you have any questions? Any questions about your assignment? Any questions about the previous lectures? Please. I talked to a bunch of people last week, at the end of the week, who had a couple of questions about their assignments. So we tried to fix the problems they had. But yeah,
I have a question.
Yeah.
For the upcoming assignment due on Wednesday, would it be enough to just use the piezo and the buttons and the force sensitive resistor?
Yeah, sure.
Okay.
Yeah. I mean, I'm going to talk a little bit about that today, just before we start today's lecture. I don't know, I figured there are a couple of things I wanted to talk about lab 4 and the corresponding assignment, but yeah, like touch sensor, piezo, and button, that works, you know, like no problems with that. You know, like once again, like what really matters in 250A is more the fact that you should be creative and to try to come up with some like interesting concepts and ideas, like for your homeworks and for your final project. But we don't care too much about like the technical aspect of what you're doing, you know, like so as long as you meet the basic requirements for that, then we'll be happy basically. So yeah. Any other questions? Okay, well, there are no more questions. Then I'm gonna say a couple more things about this week's assignment. So because I got a couple of questions that actually got me not worried, you know, like, but like what people were trying to do for this homework, you know, like, so I just wanted to clarify a couple of things here. So the first thing that I want to say is that one thing that is super important in this assignment and in this lab is the starter codes that we're giving you, you know, like, so I'm sure you already looked at them, and I'm trying to download them on my computer. Yeah, I'm just gonna open the archive here. Okay, so the point of using these starter codes is that they all have an audio input in FAUST, okay? And they all act as resonators. So as something where you send audio into it and then it resonates in one way or another, you know, just like a guitar string, or just like, you know, like a djembe or a bell, or, you know, like any of these examples is something that resonates when you actually send some kind of audio signal into it, right? So the most basic example here is the first one here in this list, and it's the comb filter, right? And so for those of you who don't know what a comb filter is, basically a comb filter is just a filter whose frequency response looks like a comb, you know, like for brushing your hair. So so basically it has like a very like typical sound, you know, and we're gonna very briefly listen to it now, you know, like, so I'm just gonna copy the content of this file, and then I'm gonna put it in the FAUST web IDE. Okay, why can I not? So that's one of the annoying thing of using Zoom on Linux. There are a lot of bugs. So okay, and I wanted to go in the FAUST web IDE, and I'm going to paste the file that I just copied here. Hello. Okay, why am I having all these issues? Maybe it's because I'm using Firefox and okay, no, there we go. Okay, so I'm gonna paste yeah, the file, and so this is comp.dsp from the starter codes. And basically, if you look at the block diagram here, all it does is that it takes an audio input. So there's one input. Then there is a multiplier here, which is your in gain, and it's multiplying the input signal by in gain. You know, and it allows you to control the gain of the audio signal that you're sending into the filter. And then here you have a DC blocker, and I think this is part of the lab. You know, I'm already explaining what the DC blocker is doing, but the DC blocker is basically preventing from having any DC components in the signal. And DC is basically when your signal is not centered on 0. You know, like it's like if your signal is centered on 0.5 or minus 0.5, then there is a DC component. And since piezo contact microphones tend sometimes to create DC signals, you know, like we put a DC blocker here, and then there is the comb filter. Okay, so the thing to just know about this example, you know, once again, is that it has an audio input. So if I run the program and if I use the built-in audio from my computer, okay, I'm just gonna turn off the volume here. So okay, sorry, that example is only mono, so I'm gonna turn it into stereo here. And I'm gonna try to increase the volume on my computer. So here, I'm gonna tap the microphone on my computer. Right? And then if I increase the feedback, I need to be careful with that. There we go, because it's going to create feedback, obviously. But now I have an instrument which basically sounds like some kind of string, right? And if I use the microphone, I can actually drive the resonator with an audio input, which here is the microphone. I can control the pitch of the sound that I'm producing, right? And so once again, here I'm using the built-in microphone of my computer, but on the Teensy, if you use the piezo, you're gonna be able to basically drive this resonator, and this is gonna produce a sound, and you're gonna be able to change the pitch of the sound by changing the delay of the comb filter here. And so the main point about this homework, the homework which is linked to this lab, is for you to play with this kind of concept, okay? The concept of basically using an audio signal to drive some kind of resonator and basically come up with some kind of instrument based on this idea. And so this is really what we kind of want you to do here for this homework. And so I know that some of you tried to use the piezo to control something. You know, like basically use the piezo as a controller or as a trigger or something like that. You know, and that's definitely like one way to use the piezo. But once again, like what we'd like you to try to do here is to use the signal from the piezo to drive a resonator, because as far as creating a new cool musical instrument is concerned, this is a very interesting way of using the piezo and the signal you're getting from it. You know, and once again, all the examples that are like all the starter codes that we gave you here, they're sort of using the same principle. So just to have a very brief look at the other examples. So so I think, yeah, there we go. It's lab 4 here. I'm opening it. So so there is the djembe example here, and the djembe is using a djembe physical model, and that physical model can also be driven by an input audio signal. You know, like, so it's always the same idea. And what's cool here, once again, you know, is that if you use the audio coming from the piezo, you can drive this model and it's just going to sound very natural because you're driving it with a natural sound, and that's what we care about for this homework once again. Do you have any questions about that? Or I'm sure at this point you probably already looked at the examples, but yeah, any questions? Okay, so I think that's something that I'm saying in the assignment, but one thing that is important for this homework too is that so piezos are contact microphones, right? And if you want to get a good signal out of the piezo, it's better if the piezo is coupled with the material that you're using as the source. Like, so say you're putting the piezo on a coffee mug, right? If you just tape the piezo to the coffee mug, you're not really going to get like a very good coupling between the coffee mug and the piezo. And so that means that the audio signal you're going to get from the piezo is going to be pretty low, basically. And so if you want to get a better coupling, the only way to do it is to glue the piezo to the coffee mug, okay? And for that, you can use super glue. You can use any sort of glue. Like super glue is what works the best for that. And if you glue your piezo to the coffee mug, I can tell you, like, this is really going to increase the quality of the signal that you're getting out of the piezo. So, the problem of gluing your piezo to the coffee mug is that once it's glued to the coffee mug, it's probably going to stay there forever, And so what I'd recommend you to do for this homework is that maybe you sacrifice one of the two piezos that you have in your kit to just glue it to, like whatever will become your final surface to control your instrument. And but only do it in the end, right? Like like if you try to glue your piezo to the first object you're going to find, and then you figure out that the sound you're getting from it is not so good, then it's probably not going to work. So what I recommend you to do, is that first you prototype with tape, and you put your piezo on a surface, and then you tape it to the surface, and then you're probably gonna get a signal which is not so good. But once you're happy with the audio signal that you're getting, you're like, oh yeah, this is what I want, then glue it, and then it's gonna be even better. And piezos are cheap, so if you need piezos for your final project, you can order more piezo. Like one piezo is less than $1. So it's not an expensive sensor. And plus you have another one in your kit. So if you sacrifice this one for your homework, you still have the other one for doing something else, right? So do you have any questions about this? Actually, Doug said something very important here. So he was answering Harrison's question, which was, how does hot glue work? So I would not recommend using hot glue with piezos. And the reason why I would not recommend using hot glue with piezo, like hot glue works, it works like with a pistols, like you put hot glue in it, and then it heats it up like the glue, and then you can glue material with that. I would not use hot glue with a piezo, because the problem of using hot glue with a piezo is that hot glue is very soft. It's kind of a rubbery material, and this is not good for transmitting audio waves, because if you have a rubbery material, like a material which is kind of soft, it's going to dampen high frequencies, and so it's going to act as a low pass filter, basically. And on the other hand, if you use super glue, like you only need a very, very thin layer of super glue to glue something. And once super glue is dry, it's actually super stiff. And for transmitting audio waves, the stiffer the better, because basically you're going to keep low frequencies, but you're also going to keep high frequencies. If you use a hot glue on a piezo, you're going to get rid of high frequencies, and that's definitely not something that you want. So no hot glue, even though that seems like a cool option and like a practical option, basically. So, was there any other question? Or sorry, I was reading the question in the chat, so. No? Okay, cool. So if there are no more questions on this, I will just wish you good luck. And okay, one last thing that I just want to say about the homework. It's related to what I said last time, but remember that whenever you're going to try to allocate a lot of memory for your audio DSP, it's possible that if you try to run it on the Teensy, it's just not going to run because you're going to allocate too much memory. And the reason why I'm saying that again is because for these specific starter codes, and also for the kind of FALS programs are going to want to write for this homework, you might actually want to use FALS programs that involve a fair amount of memory, and so just be careful with that. Like if you don't get sound, and if your Teensy seems like it's completely frozen, it's not outputting anything in the serial ports, even though you're trying to output something, then the problem is probably that you're trying to allocate too much memory, So just deal with it, and for your final project, if you need more memory, if you need like extra reverb or extra echoes or stuff like that, we can talk about it, and we can come up with solutions. But for now, these are just homeworks, right? So we just want you to use like whatever is in your kit, but like for your final project, we can actually start talking about different options. So yeah. Okay, still no questions? Cool. So today we are going to talk about digital fabrication in the context of musical instrument design. And for that, I'm just going to open the slides of today's lecture, which are over here. Okay, so slides are opening. Excellent. So digital fabrication for musical instrument design, and mostly we're going to talk about 3D printing because, as you know, in this class, you're going to have to use a 3D printer, which is part of your kit. And so first, what is digital fabrication? So the reason why I ask this question here is because in the past, when this class used to be taught face-to-face, for real, people would not necessarily use 3D printers, but instead they would use like different kinds of digital fabrication techniques. So what are the kinds of digital fabrication techniques that we would use in 250A normally? Like I would say 3D printing is definitely like one of the main ones, but laser cutting is also another kind of digital fabrication technique that we would use a lot in music 250A. And we have a laser cutter at CCRMA in the garage, and there are many laser cutters on campus that you can find. There is one, well, there are couples at the PRL. There is one in room 36. And laser cutters are great because unlike 3D printers, it's pretty easy to predict what they're going to do. Like the problem with 3D printers, as you will notice when you're going to do your lab 5, 3D printers are kind of capricious, and sometimes they stop working. You don't really know why, and then you have to spend hours fixing it before it works again, and sometimes it's going to work for 3 hours, and after 3 hours, your print is going to start failing because the nozzle of the printer is going to get clogged or some, stuff like that. With laser cutters, you never have this kind of problem. Sometimes you have to clean them up because the lens of the laser gets dirty, but they're more predictable. Other kind of digital fabrication techniques that people used in the past in Music 250A are CNC machines, and I'm going to talk more about them later in this class. And so there are all sorts of digital fabrication techniques that we can use in Music 250A and also for digital lutherie in general. But the only kind of digital fabrication technique we're going to use this year is going to be 3D printing because of the remote format of this class. So usually with digital fabrication, you always go through these 3 steps. The first step is you use a CAD software, a computer-assisted design software to design a part. And for instance, in our case, we're using OpenSCAD or any other software you'd prefer to use. But the one we recommend for the class, especially if you've never used CAD softwares before, is OpenSCAD. So with CAD software, you design an object, and it's a 3D object, and we already did that in the previous class. And then you use another software, and that other software after the CAD software is what we call computer-assisted modeling software. So it's a CAM software. So in the world of 3D printers, people gave them a specific name, and they're called slicers, like slices, slicer. And a slicer is basically just a CAM software. And even though slicers, kind of became popular as 3D printers became popular, CAM softwares have been around for a very, very long time, like that predated 3D printers and all that era. And so for as long as people have been using CNC machines, and once again, we're going to talk a little bit more about CNC machines in this class later, people used CAM softwares. And so what does a CAM software do? A CAM software takes a 3D design or 2D design, because there are CAM softwares for 2D digital fabrication techniques like laser cutters, and there are CAM softwares for 3D digital fabrication techniques. And so they take a design, 2D or 3D, and then they convert it into instructions that the machine you're going to use can understand. So in the case of a 3D printer, the kind of instructions that you're going to generate with a slicer, so like Cura in our case, like you remember in the previous class, we used Cura to sort of start looking at how 3D printing was going to happen in this class. So Cura is the CAM software in our case, and Cura basically takes the 2D or the 3D design and converts it into what we call G code. So G, like letter G, and then code. And what G code is super simple. G code is just like a list of instructions that tell the 3D printer where it should go. And the list of instructions are basically X, Y, Z coordinates. And so basically, what G code does, is that it's going to tell the printer, okay, go to this position without printing. And then start printing, and then go from here to here, and then from here to here, and then from here to here. So basically, G code is just a huge list of X, Y, Z coordinates with specific instructions associated to them. And so that's what the CAM software is doing. So the CAM software turns the 2D or the 3D design into G code, so into instructions that can be understood by the machine you're going to use. And so, as we're going to see today, there are always parameters that you can configure when you use your CAM software. So your CAM software expects some parameters to be configured or not. You can use the default parameters in the case of the 3D printer. And these parameters will tell the CAM software how to generate the G code. And we're going to talk more about that too today. And finally, there is the digital fabrication step. And in the case of 3D printing, it's very straightforward because usually with 3D printers, once you launch the print, you just have to wait for the print to be done, like for the job to be done. And but that's not the case of all digital fabrication techniques. It's also the case for laser cutting. For laser cutting, usually you just have to sit and wait, until the job is done. But with CNC machines, especially if they are not super expensive and modern CNC machines like the one at the PRL, there is usually a fair amount of work involved. You have to change the tools, you have to do all sorts of things, like throughout the process, and so fortunately in our case, with 3D printers, we're just gonna have to press the print button and then it's just gonna happen. Cool. Any questions about that, or can I move on? Okay. So digital fabrication has been used in the field of music technology and digital lutherie for a very long time, way before 3D printers. And in fact, if you own an electric guitar, there are very, very, very good chances that the body of the guitar was actually CNC'd, because that's kind of a standard for electric guitars. Like usually you CNC the body of an electric guitar, and so in big factory, like this can be completely automated, but if you're a luthier, like someone who makes musical instruments, and you're making electric guitars, it is very likely that you're going to have a small CNC machine for wood. There are CNC machines for all sorts of material, and there are CNC machines for wood, and that's what people use for electric guitars. So this video is kind of super satisfying to watch. I really like to watch that kind of videos, and basically what it shows you is that it starts from a big block of wood, and then the CNC machine, which is basically just a router, starts basically cutting the piece of wood, and slowly you're going to see the electric guitar appearing. And I don't know, like watching a CNC machine do its job is always like so satisfying to watch, because this is really so cool. So in that case, like you start from a CAD software like OpenSCAD, and or SolidWorks or Rhino or whatever. Then you use your CAM software. You configure your CAM software to tell it what to do. And the configuration steps in the case of CNC are much more intensive than for 3D printing. And then it just does its job, and like we can watch it. I'm just gonna like speed this up a little bit, and then, yeah, in the case of the CNC machine, you have to change the tools, like to do different kind of operations. And in the end, eventually you end up with a guitar. So if you ever want to make an electric guitar, that's what you need to do. You need to learn CNC machining. And for those of you who took classes happening at the PRL, there is always someone at the PRL making an electric guitar, because that's just cool to make electric guitars, right? So anyway, we're not going to do that in 258 because we don't have access to the PRL right now, and also like the skills you need to learn to do this involve more than just 1 week of classes. So anyway. So as I said, digital fabrication has been used for a long time in the field of digital lutherie and music technology. But with the advent of DIY culture, do-it-yourself culture, 3D printers became more popular, as I'm sure you all know, and that completely changed everything, at least for us, and so basically, this printers that I'm talking about, I'm sure you've seen them somewhere, because now they're kind of everywhere, but these kinds of printers, which are super cheap, like the Ultimaker is not so cheap, but the Ender 3 3D printer that you get as part of your kit only cost $170. It's crazy, you know, because when I started my PhD at Stanford in 2012, these kind of printers like they actually like started becoming a thing, you know, like, but it was only like the beginning. And buying a printer like this, you know, like they were super expensive, you know, like you had to spend like $3,000 or $4,000, and they were like super wacky. They would like always break. You'd have to fix them like every time you would have a new print, you know, and so yeah, a long way has been travel like since then, basically. And so this happened mostly because some patents expired. And if you think about it, like the technology behind a 3D printer is super, super, super simple, because a 3D printer is basically just like it's like hot glue, right? We just talked about hot glue at the beginning of this class, and so if you take a glue gun, you know, like you could actually 3D print something by hand with a glue gun. You know, like you could take your glue gun and then you would press the trigger slowly, you know, and then you could draw something on the table like a circle. And as you are going around the circle and adding more layers to whatever you're making, you know, like basically, you know, 3D printers are super, at least this kind of 3D printers are super, super, super low tech. And so this technology has been around for a very long time now. You know, like I mean, the first prototype of this kind of 3D printers kind of popped up, you know, like in the 80s actually. And it's just that the people who made those printers actually put patents on them, you know, and they never managed to sell them, like, or to sell the technology. And it's only when the patents expired that all these DIY 3D printers started popping out. So here I'm showing you the Ultimaker, because the Ultimaker kind of became a standard across the years in the field of makers, because they are known to be like super stable, like super robust, you know, but I think it's a little bit less true now, you know, like because well, I mean, they're still super robust and still like super reliable, and well, compared to other printers, because they do tend to break as well, you know, they all break eventually, but it's just that lower end 3D printers like the Ender 3 like became so much better in recent years. And you know, like just for comparison, the Ultimaker, at least this model, well, which doesn't really exist anymore actually, but this model used to cost, you know, like 2 years ago about $2,000, and this only cost $170, you know, and honestly, like the difference in quality between this one and this one, I mean, the Ultimaker is better, but the Ender 3 is not that much worse, you know, and so this has been really like the big revolution in recent years, you know, like the cost of 3D printer is like really decreased, you know, and it's mostly because so many companies like popped up in China actually, and in factories in China, and they really like took the cost down of making 3D printers, and so that's why you can all have a 3D printer as part of Music 250A. Anyway, so once again, the way this kind of printers work is that they have a filament, right? And here on the picture, you can see the filament. It's this purple thing here, you know, and it's basically the material you're going to feed into the nozzle of the printer. And the nozzle is just, you know, it's just like heating up the filament at a temperature of about 200 degrees Celsius. And it's going to melt the filament. And then, you know, like by moving around it's an additive process, right? The printer is going to add more and more and more layers of material to the object you're making, and that's how these kind of printer works. I'm saying this kind of printer because there are many different kind of printers, of 3D printers, and they are way more expensive and fancier 3D printers that I'm not going to talk about today because we don't have time for that. But mostly here, I'm really just going to talk about these kind of cheap 3D printers that we can all get very easily on the market. Anyway, so there are drawbacks of using 3D printers like the one I just showed you, like so the one which are part of your kit. And the main drawback of these kind of printer is basically this. So with this kind of printer, like because of the way they actually make the object they're printing, is that you cannot create overhangs in your design. So it means that usually there's a way, an orientation to print objects with this kind of printers. And I'm sure that many of you here used 3D printers in the past, so this is probably super boring, but there are also people who never use 3D printers. So I just want to talk about this a little bit, so that we're all on the same page. But basically, say for example, you'd like to print this object, and this object that I have here is just the cap of my water bottle. Okay. So there is a gap at the middle, right? And it's this object. So you can easily print this object if you print it in this orientation. So the bottom, so the cover here is actually going to be the first thing which is going to be printed, and then you're going to add more material to print the rest of the object. Okay. On the other hand, if you wanted to print it upside down, so basically if you were to just, I don't want to put water on my computer keyboard, so sorry. So you could actually try to print it like this, so basically start from this, and then go in circles, and then slowly add more material, and then end with the cap here, right? Like this solid part on this object. It wouldn't work. It wouldn't work because once again, these printers just keep adding material. And if you're trying to print in the void, because that's what you're doing here, if you're printing the subject like this, if there is no support under what you're printing, then the material is just going to fail. It's just going to collapse. And then it's going to do what we see here. So here. This print, which obviously is completely failed, shows you the problem you have when you do this. In this scenario, first the printer tried to print the filament here, and then of course it just failed, and because there was nothing to support it. And eventually, one layer after one layer, eventually became a thing, but that's super ugly. You don't want to do that. So all that to say that with the kind of printers you have, usually you have to think about the way you're going to print your design. And in some cases, you're going to have to optimize your design to be printed. And with digital fabrication, it's always the thing. You cannot do everything you want with these machines. You always have to adapt the design of your object depending on the digital fabrication technique you're going to use. And printers are probably the most diligent machines in the world of digital fabrication that exist. Just to say, and so usually there are many strategies to go around that. Some strategies consist in printing your object in multiple objects, and gluing them together. If they are overhangs, so that's one way to go around the problem if you really need to have overhangs. And another way to go around the problem is to use a 3D printer that has support material. And the Ender 3D printer that you have as part of your kit doesn't have support material. So what is support material? Support material is, so 3D printers that have support materials have two nozzles. So they can use two different material. And one material can actually be dissolved in water. And the other material is the material that you're using for 3D printing your object. And so it means that the support material can be 3D printed, and just like the other material. And once your print is ready, you take the object, you put it into a bucket with water, and then because the support material actually dissolves in water, after an hour or something like that, the support material will be gone, and then you wash your design and you're done, you can also 3D print support material with the same material as the one that you're printing the object. But usually it, in some cases it works, but in many cases it's kind of annoying because in many cases you're gonna have to break it, like the support material, and it's optimized to be easily breakable, like the shape, and it's the slicer which is gonna take care of that for you. Like you don't have to worry about it. But like usually we'll leave traces, like there'll always be like artifacts on your object, which are the leftovers of the support material when you do that, and then it's more work because in some cases you might want like to sand the object, like to get rid of these artifacts on the surface of the object. So not so good, and anyway, so it's just like to sort of give you an idea of all this, and once again, this is probably super boring for some of you, but I think there are some people here who never 3D printed, so I need to talk a little bit about that. So we spoke about 3D printing parameters, and those parameters are the parameters you're going to configure in your slicer software, in Cura, for instance, in our case. There are many parameters that you can configure in a Cura, like dozens, like for a single print. But the 3 parameters that you can see here in the slide are actually the most important ones. And they are infill, wall thickness, and printing speed. And just to sort of give you an idea what they are, I'm just going to show you the next slide, which sort of shows you what we mean by infill. Okay, so when we're going to configure Cura, and in fact, let me share my whole screen, and I'm going to open Cura to just show you what I'm talking about here. So okay, so this is my whole screen, and I'm going to start Cura. And once again, in order to use 3D printers you have in your kit, you're going to have to install Cura on your computer. And so infill is a parameter which is going to allow you to control the amount of material you put into a solid object. So, so say, for example, you want to print a cube, okay, like a perfect cube. You actually don't want to put material inside the cube. You just want it to look like a cube, like with solid surfaces, and no holes in it. But you don't necessarily want the cube to be like completely full of plastic, because it will make it heavier. It would make it way more expensive because you're going to have to use more plastic to make the object. And it's going to make the print time much longer, right? So you very rarely need to print a solid object, like which is completely filled with material. So when you print a cube, instead you basically ask the slicer software to create some kind of structure inside your object, which is going to support whatever goes on top. So if you 3D print the cube, when you arrive in the end, and you start like printing the last face of your cube, you don't want it like to fail, like because of the overhang I was talking about, and also you want your cube to be like solid, like you don't want it to break when if it just fell on the floor, and so for that you want to 3D print some kind of structure inside the cube, as opposed to have like solid material, and usually it takes the shape of a honeycomb structure like the one we see here, and the infill parameter will allow you to control like basically the size of each honeycomb, and like the more like the smaller the honeycomb, the more you're going to have, and the more solid the object is going to be, and the more expensive and the longer it will take to print. So if you go in Cura, you see that in the basic print settings, that's actually the main parameter you can configure here. It's the infill. So basically, as you will increase the infill, you will increase the amount of material you're going to put inside objects. And by default, it's 20%. And 20% is pretty good. So in most cases, the default parameters you have in Cura will be enough for that. And in some cases, especially if you want to 3D print musical instruments, which include some kind of resonating body, like say you want to print like, I don't know, a violin or something like that. If you 3D print the body of your violin, then you want to set the infill to 100%, because you don't want to have a honeycomb structure in something that is meant to be used as a musical instrument, because who knows what this is going to do, basically, right? So I would say this is probably the only exception where you don't want to use like a smaller infill for your object. Like if you're 3D printing a musical instrument, you will probably need to have 100% of infill if this musical instrument is meant to be used as an acoustic musical instrument. So infill is one parameter. I talked about walls thickness, and walls thickness is basically the thickness of the walls of the cube that you see here. Okay, so there is also a default parameter for that in Cura. You should probably not worry too much about it. And like the thicker the walls, like the more robust and the more solid the object, so you always have to find some kind of compromise. But what you have to know is that the plastic you're using for 3D printers is usually PLA, polylactic acid, and or ABS, and both are super stiff and super robust. So you never really have to worry too much about like the robustness of a 3D printed object. Like usually they're actually pretty stiff and pretty unbreakable. Like because they are like very robust plastics. Printing speed. That's also something that you can configure in Cura, and like. Printing speed for 3D printers is just the same as printing speed when you print some document on a regular printer. If you increase it, the quality of the document is going to be lower, and if you decrease it, the quality of the document is going to be higher. So as usual, it's always a question of compromise and finding a compromise between like printing speed and the quality of your design. Okay. Any questions about that? Or I know this is all like super abstract, but this is just like to sort of give you an overview of 3D printing, and mostly, like you're just gonna like learn how to use your printer by yourself, like, and the goal of this class is not to teach you like 3D printing directly, like, so we're gonna give you all the material you need to actually learn how to 3D print. But we're not going to like tell you like in a proper lecture like how to set up the printer and everything, because it's already done as part of the tutorial that we're going to give you. So anyway, any questions? Okay. So now I'm going to talk a little bit about 3D printing in the context of musical instrument making. So, okay, so I would say the first examples of 3D printed musical instruments are electric guitars, and I'm talking about 3D printed musical instruments at a professional level, because people in academia have been using 3D printers for a while to make like prototypes of musical instruments, like exotic musical instruments, but at a professional level, people use 3D printing. Like there are actually luthiers now who use 3D printing, and the first people who use 3D printing for industrial application in the field of music technology are people who make electric guitars, and so this is an example here of an electric guitar that you could probably only make with digital fabrication, because its shape and the structure which is inside it would be like so complicated just to make, like, and while with a 3D printer, you can actually 3D print all these parts and then assemble them together, and not something that you would be able to do with a CNC machine. And so there are many examples of guitar manufacturers, electric guitar manufacturers who use 3D printing. You know, and Olaf Diegel is probably the first one of them. Like not the first one, like I mean, like the best one. You know, like but like he's I think one of the first person who created a business around 3D printed electric guitars, and I think he's based in New Zealand. And you should go on his website. There is a link here in the slides. He does like crazy stuff, you know. Like, I mean, each electric guitar is different, you know, and it has like crazy shapes. And anyway, so before I continue, I just want to say that 3D printing has been way more successful in the case of electric guitars than in the case of acoustic guitars. And can someone guess why? You know, I expect an answer from you now, please. So why is 3D printing like better in the case of electric guitars than in the case of acoustic guitars?
Yeah, probably what Clara said. There's probably really specific engineering requirements for acoustic guitars to make them resonate, whereas electric guitars are more, you just need the pickups and the strings to make a guitar sound.
Absolutely. And so so that's exactly the answer. So in an electric guitar, the body of the guitar doesn't play a very big role in the sound that is produced by the guitar. So so with electric guitars, you can really just like give it any shape, basically, you know, and it's not going to impact the sound of the guitar much. Like what matters a lot in an electric guitar is the pickup that you use, and also the bridge of the electric guitar, and the kind of strings, you know, like that kind of stuff, you know, like but basically the body of the guitar doesn't really play a role in the timbre and in the playability of the sound. So so on the other hand, with an acoustic guitar, the body of the instrument plays a huge role in the quality of the sound that you're going to produce, you know, and you know, well, I don't know if you know, like, but literally, people really spend like years and like centuries like learning how to perfectly master the material and the shape of the material to achieve like a very specific sound, you know, like think of Stradivarius, you know, like, or like that kind of instrument, you know, like, so there is really like very precise things to control when it comes to make actual like acoustic instruments. And so so that's the next examples on the slide. You know, it's actually a 3D printed acoustic guitar. And so so the 3D printed acoustic guitar that you see here is to my knowledge the first one that was 3D printed and that is like fully assembled. And it's pretty old now. It's from 2012. And it was 3D printed by Scott Summit, who's in Silicon Valley, and he's one of the first person who created prosthetics like for medicine with 3D printers. And he created a company with that, and then probably made a lot of money, and then he sold the company, and then his next idea was to create musical instruments with what he knew, you know, like, which was 3D printing. And so the cool thing about Scott is that he actually had access to very high-end 3D printers for 2012. And so he was able to 3D print a full-size acoustic guitar as one piece, you know, and very few people like had access to that at the time, you know, and those are a little bit more common nowadays, but they're still like super expensive. And so so he had multiple prototypes of them, and so this one is the final prototype, And even though the body of the guitar is 3D printed, the neck of the guitar is actually made out of wood, because in his first design, he had a plastic neck. But then he realized that the tension of the string was too high when they were tuned, that the guitar would actually bend over time, you know. And of course, that's not something that you want. And so basically, in this example, the only 3D printed part of the guitar is the body of the guitar. And at the time, it was super expensive to make. Of course, you know, like just the material to make it was very, very expensive. And so, you know, it was a decent guitar. Like, it played okay, you know, like, but it was not the greatest guitar in the world, you know. And there are still some. I think most luthiers will not use 3D printing for now to make acoustic musical instruments because you know, it's okay, you know, like, but it's still plastic, you know. And even though like a lot of progresses have been made towards using 3D printers to create acoustic musical instruments, it's still like hard to actually make very good 3D printed musical instruments, which are acoustic musical instruments using this kind of technique. So I recommend you to have a look at the website here because Scott has more examples of instruments that he made using 3D printing, and they're all like all well made, you know, and beautiful, you know, like, and you can see like that the design here, this guitar is pretty unique, you know, because basically the bridge of the guitar is embedded in the body of the guitar. And, you know, that's something that you would not be able to make with an actual acoustic guitar, you know, like, or with a wood guitar, because you know, like, you cannot create that kind of shape with wood. Basically, it would be like too complicated and probably too fragile as well. So yeah. Okay, this is much more like downscale thing compared to this example, you know, but this is a 3D printed ukulele. And the reason why I'm showing it to you, because a couple of years ago, there was a huge trend towards 3D printing ukuleles, you know, like people, I don't know, there was really a thing on the web, you know, like, and people started 3D printing ukuleles, and it was very easy to find all sorts of design of ukuleles. Which were 3D printable. And the thing with ukuleles is that because they are so small, the body of the instrument doesn't play a huge role compared to a guitar as an acoustic musical instrument, you know, like. And so I would say like that the defaults that you get in the instruments because of the use of 3D printing are not so important compared to what you would get with an acoustic guitar because of the small size of the instrument, you know. And also people are used to hear shitty ukuleles because you can buy very bad ukuleles for very, very little money, you know, and so people are used to that. And I hope Steve Sano doesn't hear what I'm saying, because maybe he would get mad at me like for saying all this, you know, like, but like they are super high end ukulele, but the one you get on you get easily on the market for like $30, you know, like they're not so good. So and that's the kind of ukulele you would get with a 3D printer. So along the same lines, some people started also making open source 3D printable musical instruments. And the one I'm showing you here, I think, is one of the first example of that. And it's a project called Violin. And if you click on the link, you can go on their website, and it's an open source 3D printable violin. And you can see that you need to print it in multiple parts, you know, and the reason for that is because most 3D printers are not big enough to print it all at once. And there is also like the problems of overhangs that we talked about, you know, et cetera, et cetera. So when you make this 3D printable violin, you need to print all the parts apart from each other. And then you need to assemble them by gluing them together. And as you can probably imagine, the sound quality of this violin is not great because you know, it is a plastic violin which was 3D printed by a 3D printer, you know. So so the likelihood that this is going to make a good instrument is pretty low. And this project is you know, like probably 5 or 4 years old now, but the quality of printers has not increased enough like to improve the quality of the violin that you would print from these open source design, you know. And so yeah, you know, it's interesting, you know, because maybe it makes violin more accessible to people who would not be able to buy a violin, you know, because 3D printing this violin is probably very cheap, especially if you use PLA, you know, like, or the kind of printers that we have. But you know, they're still not necessarily great violins. So that's kind of the opposite example. So it's a very French project in a way, you know, because, but I can say too many bad things, you know, like during these lectures, because I'm recording them and then I'm making them available later on the web, you know, like, so I don't want people to get too mad at me. So I'm going to be a little bit less critical this year than in previous years, you know, like, but basically this is like a super high-end 3D printed violin, and even like called it like the 3D Various. Yeah, and so you can visit their website. I'm not even sure if they still sell them, you know, like, but they're pretty expensive. They're like $3,000 or something like that, and so they are electroacoustic violins, you know, and that's the key. Again, you know, it's like for the electric guitar. If you make an electric instrument, you can use 3D printing because then you you only need like a pickup microphone or a pickup or whatever, and the body of the instrument doesn't play necessarily a huge role in the quality of the sound that you're producing. And so it's the case for this violin here. You know, it's an electric violin, so you don't have to think too much about the body of the instrument, and you can really just give it the shape that you want and make it just like a beautiful object, beautiful, expensive object. Okay, so here's a more more involved example, you know, and one person who really pioneered the use of 3D printing for musical instrument is Amit Zoran, and I think he was at MIT, but I'm not completely. I think he was at MIT. I think he was at the Media Lab at MIT. And so his goal was really just to try to make woodwind, well, here in this case, woodwind instruments using 3D printing, you know, and then for that he used like super high-end printers, and he really like had to design perfectly like the shape of the keys and everything, you know, like, and then assemble them just like you would assemble like a flute like this one, you know, and so those are super interesting, you know, like, and but unfortunately they don't work so well, you know, and I think it's something that many people who try to use 3D printing to print acoustic musical instrument faced, you know. It might seem like a good solution, but in the end, like, musical instruments are so picky, and you just need like one tiny small change, you know, like in the instrument to completely change the way it's going to sound. That you know, I think a lot of people have been frustrated with that, you know, and as I said, you know, in a way it's hard to replace the skills and knowledge that luthiers took centuries to acquire, and think that digital fabrication technique just out of the box is going to be able like to replace, you know, and unfortunately it's not the case yet, at least. Okay, that project is very interesting. So, you know, on one hand, we had Amit Zoran, who really just tried to make a standard flute using 3D printing, and here we have this project from Australia, and they wrote a bunch of papers, and I recommend you to you know, just to read the paper and to have a look at the other papers that they did, you know, like, but what's interesting in this project is that they try to create an instrument that they would not be able to create otherwise than with 3D printing, and so what they did here is that they made a physical model, like a mathematical physical model of the flute on their computer to try to compute the position of the holes on a recorder flute, you know, like the one you see here in the picture, to create like microtonal flutes, you know. And so the cool thing about this project is that you can create your own tuning for your own flute, basically. So each flute that was made as part of this project has its own tuning, and it could be like a microtonal tuning. Like, so in that case, you know, it really makes sense to use 3D printing. You know, it's a rather old project too now. You know, like it's from 2016. You know, but I think it still like remains one of the standard in the field. You know, and that's why I wanted to talk to you about it today. So anyway, there is a paper, once again, linked to this project, and I invite you to have a look at it. Just click on the link, and you will be able to open the paper. Okay, here is a weirder example, and because it's weird, it was made by our own John Granzo. So I'm going to talk more about John Granzo later. You know, but you know, John Granzo, we already talked about him during this class. You know, like he was a PhD student at Carmel a while ago, and also a very good friend of mine. And he used 3D printers extensively throughout his PhD to create musical instruments. And his approach was always to create like novel things, you know. And so this this instrument is beautiful, and it's pretty unusable. So it's more like a beautiful object that you put it on a table, you know, like on display, because you can't really make music with it, but it's beautiful. You know, it's basically this bended flute with, on one hand, a flute mouthpiece, and on the other and a trumpet mouthpiece. And so I don't know if it's not a very COVID-friendly instrument. You know, like you probably don't want to like have someone play on one side and someone play on the other side. You know, and it probably doesn't work either. But you know, like depending on the time of the day, you might want to use the trumpet side or the flute side to play. And John actually did this project with Marlo Kahn, you know, like who's still at Stanford, and I think who's managing the PRL now, but I'm not sure about that actually. But she was managing Room 36 for a while, but she's still involved like in the D School and all the projects around that. Okay, here's another example of what John Granzo did with 3D printing. And this thing that you see here is a Daxophone. And believe it or not, but Daxophones are a thing actually. And there are many people, well, not me, maybe not many, but there are people in the world who own Daxophones. And so Daxophones have a tongue that you see here. And the tongue is usually made out of wood, and depending on the shape of the tongue, when you bow it, because the goal is actually to bow the tongue, you will produce a sound, and then you have a piece of wood that you put on the tongue to change its pitch, you know. And of course you have this passive amplifier here, which amplifies the sound of the Daxophone. And John Granzo made a lot of 3D printed Daxophone tongues, you know, and of course he owned a Daxophone. And that was another use, you know, like in a kind of pioneering work in that sense too. We already talked about the Javelele of John Granzo, and you know, it was part of the recycling approach that we talked about at the beginning of this class, you know, like where he repurposed this espresso percolator and turned it into this Javelele, basically, you know, like by 3D printing a neck for it, and also 3D printing a bridge and some kind of surface that goes on top of it to create a resonator. And so that's another use of 3D printing. Some people have been exploring also the use of 3D printing mouthpieces, and now there are even like companies that do that, you know, like where you can sort of order your own mouthpiece or customized mouthpiece if you're a saxophone player, or if you're a trumpet player, or if you're a clarinet player. And so there are a couple of companies that actually made a business out of that. And Karma was actually one of the first places where people like started printing mouthpieces, like way before that. So anyway, that's another interesting news. So this is a project of mine actually from like 10 years ago, maybe even more than that now, and where we were trying to create some kind of weird hybrid instrument. So basically, here you had a saxophone mouthpiece, and there was a piezo like mounted inside the reed of the saxophone, so that it would actually pick up the sound produced by it, and that's what the cable that you see here is for. It's basically just the cable of the piezo, and then here on the other hand, you had a speaker which would actually do active control on the reed. So we would actually try to change the frequency of vibration of the reed depending on a physical model running on the computer. And so basically a part of the instrument here was in the physical world, it was the mouthpiece. But then on the computer and through an interface that we made, we had the rest of the instrument, which could either be a saxophone or a clarinet. And it worked, but it was not great to play because it was so unpleasant to play. Like I played saxophone for many years, and so this thing was creating like so much vibration in your teeth that like if you played it for more than 2 minutes, like you would get like a giant headache, because you were just and so it worked. Like we managed to do active control on the reed, but it was a completely unplayable musical instrument, so it was nice. We made a paper, and we made like some interesting discoveries, but it was completely unusable as a musical instrument. So yeah. Okay, and here's the last thing that I wanted to talk to you about in the field of 3D printing for music, and it's the fact that some people, and John Granzo pioneered that too with Fernando Lopez Lescano, actually use 3D printers themselves as musical instruments, because the first thing you notice when you use a 3D printer is that they actually make a beautiful sound, and it's very musical, when they print their object. It's like, a little bit like the old needle printers, like they make beautiful sounds. And so what John and Fernando did is that they mounted piezo microphones on a printer, and they also mounted the printer to add like more things to play with it, and they made a piece here which is called Voxel, and I think it was one of the first pieces that was using 3D printers as musical instruments. And after that, some people went even crazier, like they actually made a MIDI to 3D printer converter, for a specific kind of printer, and so basically the 3D printer would have a MIDI input, and then you could play songs through the 3D printer, and of course it would not print anything. It would probably break it. But here, like what's cool is that the printer is actually printing something as the piece is being performed, and so I'm just gonna play it to you. So you see that the printer has prosthetics on it that were printed by the printer itself. Okay, we want the printer to print something. There we go. Anyway, so this is the idea. I was laughing because like this actually reminded me of like once John and I went to a conference in Athens in Greece, and we went there together, and we rented an Airbnb together, and so at like 2 a.m. Because John couldn't sleep because of jet lag. I don't know, he started using this knife or whatever it was, like on the living room table in the Airbnb, like at 2 a.m., and then it would just like hear, and I don't know, that was kind of weird. So, just some random memories. Anyway, so before I take questions about today's lecture, because we're kind of running out of time, there is one thing that I want to do for next Wednesday. So this coming Wednesday, I think I'd like you to try start thinking about final project and to all come up with 3 different design ideas for a potential final project. And they. You can draw them or you don't have to draw them, but on Wednesday, we're going to talk about final projects, and we want all of you to present at least one idea of a potential final project. And it doesn't have to be your final project, it can be just like something completely weird that is completely impossible to do. And in fact, I will encourage you to do that. Don't think about what you can do, but think about what you want to do, and then depending on what you're going to present, we can sort of, guide you towards actually making the project. But yeah, so please for Wednesday, try to think about 3 different final project ideas that you'd like to implement in this class, and have them ready to be presented in class. And if you have drawings or stuff like that you want to show, please have them ready as well. And so that would be great. And it's completely open-ended. And your 3 ideas can all be impossible if you want. That's okay. But it'd be nice to have at least one idea which is doable, though, like that. That would be great. But yeah, think more about the creative process, than the feasibility of the instrument that you will present. Anyway, do you have any questions on what we talked about today, or about any other thing related to this class? Or yeah, please.
I had a quick kind of logistical question about the lab. So I noticed in the lab you use a coaxial cable, but I noticed that the cables provided to us actually have 3. There's a red and a white, and the shield. So I was wondering how we should plan to solder that to the piezo.
Oh, because they are they are stereo cables. So,
yeah, I think they're actually stereo cables. Yeah.
Okay, so it means that so it means that well, I know your cables are actually 1/4 inch. Oh, okay. Well, there we go. Thank you. Okay, so that is a very good question. I didn't realize that those are actually stereo cables. So can you show it to me again, just to be sure? Okay, so all right, just to be sure, and maybe I can check that. I don't have the kit with me right now, so I can really well, and I don't have the cables because they would not ship to Europe. But anyway, the first thing you need to make sure is that the red wire is connected to the top pin of the cable. Yeah, there we go. And yeah, absolutely. And so so to do that, you can use your multimeter, and your multimeter can actually try to probe the wire to see how it's connected. Anyway, so the main idea here is that if the red wire is connected to the maybe Doug can do that just to check. I can't because I don't have the cable. So but Doug should have access to one of these cables just to be sure. And so the red wire I think should be connected to the top pin, and then you want to connect the two other pins together. Okay, so basically, yeah, there we go. Yeah, absolutely. So so probably the white and the blue together and the red alone. But that's only if the red is the top pin. If white is the top pin, then you have to do it the other way around. Like so, red with blue and white alone. But I think red should be the top one. So but it needs to be tested, and unfortunately, I don't have access to the cable, so I can't test it. So so Doug can maybe do that quickly, or if you don't know how to do this.
Let's see if I can find my multimeter real quick as well. But anyways, yeah, thanks. That's really helpful.
Yeah, sure. Any other questions?